When you think of a big number, what pops into your mind? A million? A billion? Maybe a trillion? We hear these numbers tossed around all the time. $1 million supercar, $1 billion skyscraper, $1 trillion tech giant. But compared to the true titans of mathematics, these numbers are practically nothing, like a grain of sand next to a galaxy. A trillion is just a 1 with 12 zeros, expressed with a 10 to the 12th power. Let's crank things up by doubling the orders of magnitude to a septillion, that's 10 to the 24th power. Double them again to a quintillion, or 10 to the 48th. We can keep going all the way up to a vigintillion. At these scales, the numbers become so large that without the right perspective, our minds simply can't grasp them. Considering this, let's look at our first truly giant, 52 factorial. Expressed as 52 with an exclamation point, it is the number of different ways a 52-card deck can be arranged. This number so large that no two properly shuffled decks have ever been arranged in the same order since the invention of the 52-card deck in 1480. Already mind-bending, right? 52 factorial is derived by multiplying 52 times 51 times 50 and so on and so forth, all the way down to 1. As humongous as 52 factorial is at 10 to the 67.9 power, it is still 12 orders of magnitude smaller than our next giant, Eddington's number. Named after British astrophysicist Arthur Eddington in 1940, Eddington's number, 10 to the 80th power, is the estimated number of elementary particles in the observable universe. Next on our list is a Googol, written as 10 to the 100 power. To give a sense of how massive a Googol is, imagine filling up every empty space of the observable universe with sand. It would still only equal 10 to the 95 grains. The number would have to be 100,000 times bigger to make a Googol. As far as big numbers go, we haven't even made a dent yet. Let's crack it up another notch. Meet Shannon's number. An estimate of about 10 to the 120 for the total number of possible chess games, considering the branching at every move based on each player, having roughly 30 to 40 choices per move over 40 moves. It shows how incredibly complex chess is, far beyond brute force calculation. It was proposed by Shannon, the father of information theory, in his 1950 paper Programming a Computer for Playing Chess. As massive as a Googol and Shannon's numbers are, they are microscopic compared to a Googolplex. Expressed as 10 to the 10 to the 100, a Googolplex is so colossal, you would need approximately 10 to the 40 observable size universes to have enough space to write this number down. And even if you use 1 atom per 100 digits, you would run out of atoms long before finishing. And while a Googolplex is astronomically large, it is completely overshadowed by Graham's number. Graham's number is a mind-bogglingly supermassively humongous number, defined by American mathematician Ronald Graham as an upper bound for a problem in the field of Ramsey theory. In 1977, it became the largest number ever used in a published mathematical proof. Just when you think numbers can't get any bigger, buckle your seatbelts and meet Tree 3. Tree 3 is a super ginormous mind-collapsing number, derived from Kruskal's tree theorem. It's the maximum length of a sequence of rooted trees, where each tree uses no more than 3 seed colors, and no tree in the sequence can be embeddable into a later one. Tree 3 is so humongous, the universe would reach the big freeze state way before you can define every possible tree combination, even if you started a nanosecond after the Big Bang. If your head hasn't collapsed into a black hole yet, let us introduce to you the undisputed heavyweight champion since 2007, a truly titan in the world of big number theory. The top dog, the big kahuna, numero uno honcho, the head cheese, the one and only, Rayo's number. One of the biggest finite numbers ever imagined by humans, Rayo's number was defined by Mexican philosophy professor Agustín Rayo during a big number duel at MIT on January 2007. In simple terms, Rayo's number is defined as the smallest number bigger than any finite number named by an expression in the language of first-order set theory with a Googol symbols or less. The formal definition of the number uses second-order formula. In essence, Rayo's number exploits the limitations of formal language to leap beyond what can even be named, making it a towering giant in the hierarchy of large numbers. Finally, we reach the summit, at least for now until someone defines an even bigger class of number. What's most fascinating is the fact that even the most ginormous numbers featured in this video are still finite, meaning despite their size they all end at some point, which means they are practically closer to zero compared to infinity.
Inspired by this video, get your mind-bending finite number t-shirts, baseball caps and mugs exclusively at Geeky Gear Designs. Head over to our Etsy shop to find unique math and science-inspired designed gear and great deals. Do not forget to like and follow.